Hello everyone, this again is Miss Crane for Chapter 17, so our part 2 of our review session posted on today, Tuesday, March 10th. So, we're going to jump right into Chapter 17 and hopefully watch my other video for any other hints that you may have on how to study, right? So, my other video gives a bunch of hints on that, on what to how to study and everything, and if you come to my review sessions you know that as well. Okay, so today we're doing Chapter 17 and we'll start off with the first question. Again, if you want to pause the video for a second, I suggest you get out your workshop or at least the answer key printed off from the internet if you don't have it on you. So let's jump right in. So for number one, hopefully, okay, good, you can see that, hopefully. It's a little, the video's a little, what I can see is a little smaller than you guys can blow it up on, expand it on YouTube, full screen it. So we say, consider the equilibrium of B aqueous. And we always know that's a liquid, H2O. A lot of times I do not, if you've never watched one of my videos, you know, a lot of times I do not write the aqueous there because I run out of room, as you can see right there. But just know that almost everything is aqueous except for water, right? That's normally the liquid. Now, this is talking about, the first problem is talking about Le Chatelier's principle. Explain the effect of the presence of a salt of Hb plus on the ionization of B. So, now, anytime you add, so the biggest trick to this problem is anytime you add something to this side, it's going to shift the equilibrium to produce more of this side. So you add something more to the products, it's going to shift the equilibrium over to the reactants, and then vice versa. You add more B, it's going to shift it over more to the product side. Okay, so that's the biggest thing. So here it says, explain the effect of the presence of a salt of HB, so they're telling me that's my salt, on the ionization of B. So basically all you're saying is that I'm increasing, if I'm adding more of this, it'll shift the equilibrium over to the left side, or the reactants. You can say left side or reactants, either way is fine. And then that will cause the ionization of B to decrease. So what does it mean, the ionization of B? So for B to be ionized, it has to be in ion form, right? So I'm taking this boron and I'm making it ionized. So it's asking, this process of B becoming ionized, what's going to happen to it? I hope that makes sense. Sometimes these words, the wording of questions can be very difficult to understand. You guys at least understand that if I add more of this, it's going to shift it left. So I add more of a product, I'm going to shift towards reactant. The ionization of B becoming ionized to a plus, this is a plus right here. This occurrence right here means that it will decrease. The ionization of B becoming an ion, will decrease because I added more of this. So that's the basic definition of what this question is asking. So the ionization, this becoming to this, will decrease because I'm adding a bunch of it and it's shifting it over to the left. If I'm adding more of this, I'm getting less of this to produce that. Hopefully that makes sense. I know it can get a little confusing, and hopefully you guys can see everything all right. Oops, sorry. I'll move the computer up just a little bit. But again, I know you can expand it on YouTube. So part B, that's part A. This is added, the left side, the equilibrium shifts over here, and then the ionization of B becoming an ion, decreases. That's the answer. Part B, give an example of a salt that can decrease the ionization of NH3 in solution. So, again, the question, give an example of a salt that can decrease the ionization of NH3. So basically, we'll be looking at this right here to come up with this next part. So we want to decrease the ionization. We want to not have NH3 become an ion. And what is NH3's common ion? It's NH4+, right? You guys have seen that quite a bit, NH3 and NH4+. So we can just throw this in liquid or water like we always do, and it forms that NH4 plus OH minus. Because this is a base and this is weakly acidic, right? Weakly basic, weakly acidic. So any salt with a hydroxide group will cause the decrease of ionization of NH3. So just like we said, increase here will decrease the ionization, and increase here is going to decrease that ionization. So they wanted you to be able to apply what you knew here to the next problem. Okay, part number 2. Calculate the percent ionization of, so we're looking for percent ionization is what we don't know. And now we're looking for percent ionization of, and what's given to us is what I meant to say, 0.0075 molar of butanoic acid. What did I say in my last study session, online I mean, about anything we saw as COOH? If it ended in CO, so it's connected to something else. So if it ends in COOH, it's weakly acidic, correct? So that's the first thing. It says butanoic acid, and it does not give us the actual formula. But anytime I see oic acid, ethanoic acid, butanoic acid, hexanoic acid, anytime I see that oic, like it's at the end, like hexanoic or butanoic in this case, oic acid, that means it's that COOH. So we first assume that this is a weak acid. And remember what I told you about weak acids versus strong acids. Weak acids, you're going to have to set up that ice chart. So again, this is fairly easy to figure out that it's a weak acid. You just needed to remember that when you have that oic acid, then that is the COOH at the end, which makes it weak. Now, do I actually have to know to solve this problem what butanoic acid's full formula is? No, technically I don't, but I do need to know this, because this is the important part. This is the acidic hydrogen that we'll need to work with. So as long as I know oic acid ends in that, that's all I really need to know. And I'll show you exactly what that means when setting up our ice chart. So again, I see a weak acid, I immediately think ice. Okay? So now, what do we normally do when we set up an ice chart? We actually make whatever molecule we're using ionized. So instead of writing out what butanoic acid, let's say you forgot that butane had 4 carbons and then hydrogens around it. So that's what would be connected to here. But say you forgot that butane had that. Well, you can just literally write butanoic as Bu. That's what they did on this answer key. You can just say that. That's shorthand, and actually chemists use that all the time, that shorthand. Instead of writing out a full formula, they use shorthand notes. So you could say butanoic, or this stands for butanoic. So you actually only needed that COOH. That part right there is just shorthand for butane. Okay? So now, I have this, and what do I normally do? I throw something in water, but we don't ever include water in our ice charts or our equilibrium expressions, the Ka expressions. So here what I do is I throw it in water. I'm going to leave water out. I did an example on chapter 16. So I'm going to leave water out, and then I'm going to split it up. H plus and BuCOO minus. So does everyone see what I'm doing here? Hopefully. You saw that, okay, when I throw this in water, this is my acid, this donates. So basically, all I really need to show, this donates to the water, creating H3O+, right? And remember, what did I tell you? H plus and H3O plus are exactly the same. If you wanted to write this formula as this plus water with H3O plus and then this ion forming, that is completely fine. This is shorthand. I just want to show it to you because teachers use the shorthand all the time, and you'd be like, well, what happened to my H3O plus? What happened to the water? It's assumed to be there, okay, guys? Don't freak out if they write it like this. It's exactly the same thing. I know a lot of people get confused because there are a lot of shorthand. I had a lot of trouble, too, when I was first in chemistry, understanding that these two things meant the exact same thing. Not writing water means it's assumed there. Yeah, that's confusing. I get it, but just assume that it's there, okay? That's why I keep, reiterating it over and over again about it. Anyway, so this is the shorthand version of it. You want to write the whole thing out? Fine. Just in your ice chart, cross out the H2O. Now, the only two things given were this. Well, actually, this was the only thing given. It's asking for percent ionization. It was not given to us, right? So we're only given this. So now we set up our ice chart. Initial, change, equilibrium, right? So initially, the only thing that's given to us is this. So this is a pretty basic one that we've done, in chapter 16. Initially, I have, so therefore, what do I have? If I have not mixed this with water yet, I don't have anything for products, right? Initially, we're not mixing anything. So we're saying all products are 0. Now, that's the only thing they gave me was an initial value, so I assume my change is just X, right? Again, my reactants are always going to be depleted as the reaction occurs, and products will be formed. And then my equilibrium value are just the initial plus the change. So I just add these two values together. This gives me that 0.0075 minus X, just plus X, or just simply X. You could just leave it as X, whatever. Doesn't matter. It's fine. Okay. So now, they also give me I didn't write that. They did give me two things. They gave me a Ka value in parentheses. My Ka is 1.5 times 10 to the negative 5. I thought they gave you two things. Anyway, so this is given, and this is given. So those two values are given, right? So this is my ice chart. Now, equilibrium expression, what does that mean? Ka. Set up my Ka. Ka is equal to 1.5 times 10 to the negative 5. And now what's my Ka expression? It's my products over reactants of the equilibrium values, right? So that's going to be X times X all over 0.0075 minus X. Right? So what was my rule yesterday? Or, I mean in chapter 16, not technically yesterday, because you could be watching chapter 16 right now. But what was my rule for chapter 16? When can I get rid of this minus X? That's when my Ka is smaller than 1 times 10 to the negative 3. So this value is smaller than 1 times 10 to the negative 3, right? It's a negative 5. So since this is smaller than that value, we can always assume to cancel that out. Don't need it. Because it's so small, that X is assumed to be so small it's insignificant to subtract it from this number, right? So, in this case, we can do the shorthand, and we can get rid of that X, okay? So what does that mean? That means, in this case, now we can find X much more simply instead of doing the full quadratic equation, right? So going back, we can say, now, moving on, Ka, which equals 1.5 times 10 to the negative 5, equals X squared just over 0.0075. Much more simple equation to solve for, correct? So now, again, we can assume this is over 1. Cross multiply. Cross multiply, get these numbers on one side. Then what x squared is equal to these two multiplied by each other. And then we take the square root, right? We take the square root of both x and this number, whatever these two multiplied by. And we should get an x of 3.354 times 10 to the negative 4. So that's what my x equals. Now, what is the question asking for? I got down to x, and a lot of people will just stop there because they're not really looking at what the question is asking, right? What you're going to do is find percent ionization. That's what it's asking for. So that means that this x, if we go back to the previous page, this x is equal to, yeah, you can see that, okay. So butanoic acid's equilibrium value will be that 0.0075 minus this x value. Equilibrium concentration of H plus will just be x, and the same thing for the ion. The ion's value concentration will also be just that x. Now it's asking for percent ionization. What you're going to do for percent ionization, you're also, just like you do for pH, say this was solving for pH. We'd literally take what H plus's value is, equilibrium value, and we'd find the pH from that, right? But in this case, percent ionization, I shorthanded it, is going to be my H plus concentration over my original concentration. Times 100, right? You have to multiply by 100. Okay? So, in other words, x. In other words, what they give you in the problem, right? So here, H plus is the 3.354 times 10 to the negative 4. And my original concentration, which was given to me in the 2A, it says what is the percent ionization of 0.0075 butanoic acid. So that was given to me in the problem. Times 100%. And this ends up equaling 4.5%. That means only 4.5% of this original acid became ions. Okay? Only 4.5%. Very small amount. So that was part A. Part B is calculate the percent ionization, so we need to do that part as well. Calculate percent ionization of the same amount, the same concentration of butanoic acid, that 0.0075, in a solution containing 0.085 molar sodium butanoate. So, this is not a very hard calculation, but a lot of people get confused. So now, we're going to set it up exactly the same way. Percent ionization solution containing that much of sodium butanoate. Okay. We're going to set it up exactly the same way. Again, you don't remember what butane is, totally fine. You can just write that COOH, butanoic acid, plus water, or leave it out. If you want to see it with water, I will write it that way this time. Either way, again, is completely fine. Let me show you again. This way with what? Well, actually, let me finish this. With water, you can write it exactly like this. That's what I was talking about on this page. Or exactly like this. It means the exact same thing, right? And then in your ice chart, you're just going to cancel out the H2O because you never include liquids in your equilibrium expressions or in your ice charts. So now, what we're going to do here, calculate percent ionization. So again, we're finding the same thing. Percent ion, don't know. We have a concentration of 0.0075 of butanoic acid in a solution containing, so this is BuCOOH, and then a solution containing 0.085 molar sodium butanoate. So sodium butanoate is something like this. We add so instead of having this BuCOOH, we have this BuCOONA. So we took off that acidic hydrogen and we put a sodium in replacement of it. That may be a little hard for some of you to wrap your mind around. But when they're doing something like this, they're assuming, so in this case, it's slightly different. We are saying that my initial BuCOOH is 0.0075. So that's normal. If you decide to write water in there, this is ICE. If you decide to write water in there, you're just going to want to X the whole thing out because you don't want to get confused by it. Just X it all out. Okay? Now, my H3O plus, or just H plus if you're using the method you did previously, that's going to be just 0 again. I'm not doing anything to that. But what is this going to be? This is a product which is normally 0. They're actually giving me an initial value for this. And I know that may be very difficult for some of you to understand, but this is an acid, this is a base. In this equation, this is my acid, this is my conjugate base, right? So I plug in whatever my base is here for my base value in this equation. I hope you guys need to practice a couple of these, not just this one, maybe one's on her PowerPoint, to understand that these two things will be exactly the same. This is the acid, this gets plugged into the acid. This is the initial base, and this gets plugged into the base. Okay? So that means this value right here, 0.085, gets plugged in as an initial value. My change is going to be exactly the same. They don't give me any indication of what my change will be, so I'm getting rid of reactants and I'm adding more products. This should be, the next few parts should be exactly the same way you've set everything else up. The only difference is that they gave me an initial concentration of a base, so I have to add it there. Okay. So now, my equilibrium values, I add these two together, 0.075 minus X plus X, 0.085 plus X. So then my Ka expression is going to be products oops, sorry, don't want that to look like a 1. Products over reactants. Okay, so now, can we use that rule that I said before? So the Ka is the same. Remember our Ka in the previous problem? This is just part B, so our Ka in the previous problem was 1.5 times 10 to the negative 5. If this is, again, smaller than 1 times 10 to the negative 3, then I can get rid of this X, right? Now, here's a trick. Anytime you apply this rule where it says Ka is so much smaller than 1 times 10 to the negative 3, you can get rid of everything that is added and everything that is subtracted. Multiplication and division will not be part of this rule. What is part of this rule is anything added and anything subtracted. So my Ka expression can get rid of both this and that. So that is one of the big, besides adding this here, this is another big trick to this problem. So my Ka expression ends up looking like x times 0.85 divided by just 0.0075. And of course the Ka is equal to 1.5 times 10 to the negative 5. Right? So again, I can solve this really easily. Get x by itself. Okay? X by itself means, once I solve for it all, 1.3 times 10 to the negative 6 molar, right? And again, this is asking for percent ionization. So I'm going to take whatever my H3O plus is, or H plus, however you wrote this equation. I'm going to take that value right here, which happens to be this, and divide by that 0.0075. So this was in the initial acid. This is my equilibrium of H plus, which also happens to be the acid, right? So, or H3O plus, or conjugate acid. Acid versus acid. So that means I'm going to take, so percent ionization will be my concentration of H plus, which happens to be 1.3 times 10 to the negative 6, divided by the acid that was originally given to me in the problem. So you want to compare acid to acid. Some people might be like, well, why didn't I use this value? Why do I know to use that? Because you're comparing acid to conjugate acid. 0.0075. And this ends up being 0.018% percent ionization. Okay? So hopefully that makes sense to you. There are a couple little tricks. In this case, it was having an initial value for a product and then being able to cancel both the plus and minus. Okay? So now, we have some like definition things here. If you look at her slides, Dr. Yang has slides about what can and cannot be a buffer solution. So number 3, it says explain why a mixture of acetic acid, which is actually what we did here. Well, this is butanoic acid and sodium butanoate, but that's the same type of thing they're asking here. Acetic acid, which is the COOH and then COONA, can act as a buffer, while HCl and NaCl cannot. Well, you have to have a weak conjugate acid conjugate base pair. You can't have any strong acid and strong base. Even though they are conjugate acid base pairs, they are strong, and you have to have weak in order to create a buffer. You have to have a weak conjugate acid conjugate base pair, not a strong conjugate acid conjugate base pair. Okay? And I'm going through these fast because they're more definition things. I want to get to the calculations. 4. Explain why a mixture formed by mixing 100 milliliters of 0.1 acetic acid and 50 milliliters of NaOH will act as a buffer. So here what they're saying is I'm mixing a bunch of a weak acid with a smaller amount of a strong base, and it will act as a buffer. Describe that to me. Now, the biggest thing for number 4 is that we have acetic acid, the weak acid, in excess. There's a bunch of it, whereas NaOH, there's only 50 milliliters, which is a good amount, but there's 2 times more the acetic acid, so it will act as a buffer because there is a weak acid in excess. There's much more of it, okay? So, number 5, let's move on to number 5. A buffer contains 0.15 mole of propionic acid. What did I say about oic acids? This is the same, well, you didn't actually have to know it for this one because she gave it to you in parentheses. the acid was given to you in parentheses. Propionic acid, it has that COOH at the end again, which is also weak, right? Anytime I see that COOH with that any form of hydrocarbons, it's weak. A buffer contains that much, so we have initially 0.15 mole of C2H5 COOH, right? And then we have 0.1 mole of sodium propionate. So we have C2H5. So these should start looking kind of familiar to you. I'm seeing that we have these COOH, and then it's exactly the same thing except COONA. Acid, base. Acid, base, right? So start getting familiar with that because she loves that. She loves that COO at the end for you guys to use that and know that it's that weak. This is a buffer equation, right? Number 5 is a buffer. So what we're going to do here, is we're going to first find, and then it tells me in 1.2 liters. So we have a volume of 1.20 liters. Part A states, what is the pH of this buffer? And then it tells me that my Ka of propionic acid is 1.3 times 10 to the 5th. You will never have to memorize Ka values. They will be given to you. Okay? So, we're talking about a buffer. What is the famous equation for buffers? Henderson-Hasselbalch, right? So, and that is that pH equals pKa plus log base over acid, right? So that should be a pretty straightforward calculation. All you have to do is take the P of Ka, right? What do we do if we put a P in front of Ka? What if we put a P in front of pH? You always say, so it says find the pH. You always just say negative log 1.3 times 10 to the negative 5 plus log of base over acid. So the concentrations of base over acid. So my concentrations are 0.15 divided by that 1.20. Right? Because we want concentrations here as moles per liter. And then, oh, I'm sorry. We want base over acid, right? This is base. This is acid. So if we want the base, we want that 0, right? We want this value over the 1.2 liters. And then acid is the 0.15 mole over 1.2 liters. So we do, we find the concentration here, find the concentration here, divide this by this, get the log of it, then negative log of that. Just make sure when you plug everything in that you get the 4.69. pH of 4.69, okay? Now the next problem is saying, this is part B. I may have to go on another page. What is the pH of a buffer after the addition of 0.01 mole of NaOH? So this is a different type of, when they're talking about buffers, this is a different type of ice chart where you're actually adding a little bit something to what we already have for ice charts, right? So, and you write them slightly differently, their equation. So we're going to have C2H5COOH Now it's saying I'm adding NaOH, C2H5, COO-Na. That's what's going to be in my ice chart. I have this initially, I'm adding NaOH, and then I'm forming at the end this plus Na. And what else is the other thing? It's water, right? The other product is water, but I'm not adding it here because you don't need it for an ice chart. But this is a slightly different ice chart. What are we starting out initially? What is pH after the addition? So this is part B, where we are saying we are adding how much? 0.01 mole NaOH. So that is my addition, which means the first part I still have values, right? In number 5 it says a buffer contains, so this is given in the problem. So my initial value, buffer contains that much of propionic acid and 0.10 mole of sodium propionate, right? Propionate, 0. Now, NaOH has not been added yet. This is what we have initially. What am I adding? So sometimes they call this change, but for buffer, sometimes they call it addition. So you may have seen it called addition. And what they say here is that we're adding that 0, what was given in the problem. If I'm adding that, here, then I just say, and you can leave this chart, another thing about this is that you can leave these charts in moles instead of molarity, because at the end you're going to have to put everything over a total volume in many cases, because we're adding something extra, right? So most of the time you're doing molarity, but here we can do moles, because sometimes they want the final volume, to divide by the final volume to find certain concentrations. Okay, so now we have addition and then equilibrium. So it'll be that 0.15 plus, or sorry, minus. Because remember, anything that's, this is minus. So 0.015 minus 0.01. This will just end up being, since we're adding it in a middle step, this will just end up being that 0.01. And then this right here will still be the same, 0.1 plus 0.01. Okay? So these are a little different, right? We can put this in moles instead of molarity. We can say 0.15 moles. This was given initially for both acid base. Then we're adding more base, right? We're adding 0.01 moles. So we're calling this the addition. We still subtract. This is like the wild card section right here, right? Because at the very end, my equilibrium is still just going to be that addition. Instead of subtracting like we normally do for a reactant, we're just keeping that the same. And then this, we still did the same thing. We add to it because it's a product, and this we take away from because it's a reactant. This is just the wild card section right here. Okay? So now we can plug straight into the Henderson-Hasselbalch equation, saying that pH is equal to pKa. And remember, on the previous page, we found pKa right here. That ended up being 4.89. Plus log, and what do we have to do here? We actually have to say equilibrium of base, which is this, and equilibrium of acid. So it's base over acid, so it's this value, so that's 0.11 divided by 1.2 mole per liter. And then this is 0.15 minus 0.01, 0.14 mole divided by 1.2 liter. So we got these are the concentration of base over concentration of acid, right? So once we found those values, you can divide these two by each other, log. We already have our pKa from the previous part of this problem. And then my answer should be 4.78, right? Okay, moving on. Again, you can pause and rewind, do whatever you need. Now, for this problem 6, I'm not really going to go over it. It's talking about, if you don't remember or don't have it in front of you, it's talking about this type of chart where you just have to evaluate what the titration chart, you know, it's a titration chart where it's milliliters of base and this is the acid, and they're asking the differences between a weak and strong acid when strong base is added to both of them. I think it's pretty self-explanatory. You don't understand, her notes are pretty good on it, okay? So go through her PowerPoints if you're not quite sure. So, number 7, we're just going to do like one of them to get us, you know, testing the waters, how to write KSP, the KSP expression. Write the expression for solubility, that's its formal name is solubility product constant for each of the following strong electrolytes. So we're just going to do C, 7C. If you want more practice, you can do the other ones on your own. So 7C is iron hydroxide. KSP, writing a KSP, a molar solubility constant for this is just splitting it into its ions. It's very similar to Ka and Kb, except here we obviously don't have products versus products over reactants. We just have one molecule. So we just say concentration of Fe. What's my charge of Fe? Remember, we swap charges. Fe is a 2+. Anything listed first is going to be a plus. Anything listed second will be the minus. OH minus. Now, what is the only thing I'm missing here? In this problem, there's one Fe and there are 2 hydroxides. So I square whatever my subscript is. If there's 2 of them, I square it. If there's 3, I cube it. Okay? That's how you write a KSP. Okay, number 8. If the molar solubility product, if the molar solubility of Pb lead bromide at 25 degrees Celsius is this, what is the KSP at this temperature? So the first thing you want to do is very similar to this. This is our PbBr2. So it's very similar to this. You want to split it up into its ions. This is a solid. Pb, we should be able to Pb 2+, right? The 2+. And then plus, how many Brs are here? 2, so you have to account for that here. Br minus, but then I need to put a 2 in front of it. And these will both be aqueous. Starts off at a solid, then it becomes aqueous. So now it tells me my molar solubility. My molar solubility is at 25 degrees Celsius 10 times, that kind of looks like a 6, 10 times, or 1 times 10 to the negative 2 mole per liter, right? What is, mole per liter is what? Concentration, also known as molarity. It's called molar solubility. It's telling me my molar solubility. What is the KSP? So this is a pretty self-explanatory question. They give me molar solubility, a concentration. I should be able to plug into this expression. What's my KSP? Well, it's just Pb2 plus and Br minus squared. So in this expression, my molar solubility, Pb, There's just a 1, and a 2. PB is just going to be 1 times this value. BR, since it has a 2 in this problem, 2 times that value. So that's how, from a molar solubility value, that is how you will find both concentration of PB and concentration of BR. It's 2 times that molar solubility. So that means that in my actual KSP expression, KSP, I'm going to say 1 times 10, so this should just be 1.0 times 10 to the negative 2, times BR, so BR is going to be 2.0 times 10 to the negative 2 squared, right? That's my KSP expression where BR is squared, and that'll be my KSP. And that value is, even though you have an answer key, your answer is 4.0 times 10 to the negative 6. Okay? It asked for the KSP, so we knew we had to write out this equation. We had to write out when it split into its ions, so we knew that 2 of them made up BR minus its concentration. So that's pretty self-explanatory. I think 9 is pretty explanatory. 10 is a little bit of a trick. Yes. 10 is a little trick. I'm going to try to do 10 and 11 in the time we have left. So, number 10, calculate the pH of a saturated solution of calcium hydroxide with a KSP. So how did I know that not to use like an ice chart or do what we've done before? Well, it's giving me KSP in this question, right? So number 10, calculate the pH of a saturated solution of calcium hydroxide. Looking for pH with a KSP. And the molecule we're looking at is calcium hydroxide, right? So that means my KSP value for this is what? Ca2 plus OH minus squared. Now, in the previous problem, well, number 8, I mean, it gave me a molar solubility. There is no sort of concentration for me to work with here. So just kind of like ice charts, we put in X's, right? So my KSP here, I have no idea. I have no idea what the molar solubility is. So I'm just going to leave an X. OH, there's 2 of them. So I say 2 times X squared. It's 2 OHs. If we split this up and did the actual equation, right, so there's 2 of them. That's why we put 2 here, and then we also square it in the KSP. Alright? So that ends up giving me 4x cubed. If you, so KSB is the 6.5 times 10 to the negative 6. If you end up dividing by 4 on both sides, and then you cube this x, cube root of x, you can get x to be 1.18 times 10 to the negative 2. So now what is it asking for? It's asking for the pH. This is my X, so I can personally find OH and then transfer that to pH. I hope that makes sense, right? Because if I can find POH, then I can change it to pH. So I have a concentration. OH's concentration, the biggest trick here, OH's concentration will be 2 times this number, right? 2 times X. 1.18. Right? Because we said there's 2 of them to every 1 calcium. So there's going to be 2 times that X. And that will give me 2.35 times 10 to the negative 2. Now that I have my concentration of OH as this, negative 2, I know it doesn't really seem like a negative. Now I can say negative log. POH is equal to negative log 2.35 times 10 to the negative 2 equals 1.63. You should notice that if I'm getting an answer of 1.63 and my molecule is a base, shouldn't seem right. So, because, you know, bases are in between a pH of 7 and, as we're looking for pH. So, pH is, for bases, are between 7 and 14, right? So, this should be in between those values. So, actually, we can use this pH plus POH, POH is equal to 14. Plug in pH plus 1.63 equal to 14. 14 minus 1.63 will give me a pH of 12.4. Okay? Now, that's a pretty good one, and the biggest trick is knowing that you have to double your OH concentration as well as square it. Yes, it seems like overkill. A lot of people ask me that. Isn't that kind of like double dipping? No, that's just how you write it. So the next one, number 11, I know you guys probably want to do number 12 really bad as well. So let me see. But I've done something similar to number 12 before, and I think you can follow it. I don't think that one's that hard. There's just kind of a two-step. But number 11 I want to get to today, because I have not done this actual with you before, but it is pretty easy. So number 11. Will cobalt hydroxide, OH2, precipitate from a solution if the pH of a 0.020 molar solution of cobalt nitrate, yes, is adjusted to 8.5. Okay? So, the reason I can use these two together to find KSP, okay, this is one of these questions where you have to compare two values in order to determine if this will precipitate out. This is a common ion, so it's possible. These are common ions, so it's possible that it will precipitate, or could precipitate. So, we have, our first step is, what are we looking for? We're looking to see if this will precipitate out, right? So what we're going to do is we're going to see, since we're looking for this, we're going to split that up into its ions, like we do normally for KSP. When something is precipitated out, think of it as a KSP problem. This is what we're looking to see if it'll precipitate. So I'm going to split that up into its ions. Right, there's two OHs, so we need to account for that on the product side. What's my KSP? KSP equals